Good morning. Today, I'd like to look at the first of our actual new methods that most textbooks look at. I want to look at something called the disk method. Let's look at the premise of that. Think about the graph of y equal x squared plus 1, starting at x equal 2, ending at x equal 5. If I wanted to know the area under that graph, we know what to do. Since x squared plus 1 is positive, we would just do the integral from 2 to 5 of x squared plus 1 dx. But in our current situation, that is not what we're going to do. Instead, I'm going to grab the x-axis and use it like a handle to revolve this shape completely around the x-axis one time. Each one of these dots that I've indicated here goes around in a circle. This one goes around in a comparatively small circle. That one goes around in a larger one. That one goes around in yet a larger one. Every point goes around in a circle. If I look at what happens to the entire region, then I get some sort of solid three-dimensional shape. If I were to build that solid shape using a 3D printer or something like that, I would need a certain amount of material to make the solid, a certain number of cubic inches or cubic centimeters or whatever your units are. I'd like to know how many cubic centimeters of plastic I need to make in order to make this shape. This is not on the standard list of geometrical shapes that we know about, so we're going to have to do some thinking here. Seemingly unrelated, I want to think about having what amounts to a piece of a cylinder. It's going to have a certain circular cross-section to it, which has some radius or the other, and in the perpendicular direction, I'll just call that amount the perpendicular height. You'll remember from geometry that the area of something like this is the area of the base times the perpendicular height. Of course, for a circle with a certain radius, the radius of the base then will be pi times radius squared. If I could tell you in symbols, in some reasonable way, what the radius of such a thing was and what its perpendicular height is, then I would know how to calculate the volume of something like this. The idea that we're going to follow is this. I'm going to think of my three-dimensional solid shape and split it up into a great number of things that are more or less of this nature. I'll figure out the volume of all of those different chunks, and then we will integrate them together to get the volume that we're really interested in. The only issue is exactly how am I going to do this? What are going to represent the perpendicular heights, and what are going to represent the radii? This is what I want to end up with in my mind, but how do I get there? The solid shape that we're interested in is obtained by revolving all of the points under the graph about the x-axis, so it might be informative to split that set of points up into easier to think about sets. If I revolve this vertical strip 180 degrees 360 degrees, full circle, about the x-axis, what it traces out is a disk. If I revolve that one about the x-axis 360 degrees again, it traces out a disk. So where these disks come from, they come from these vertical strips that we're looking at. As usual, we'll chop the range of x values, the range from 2 to 5, up into a large number of smaller pieces. I'll select one of those pieces to look at, piece number I, and I'll call its horizontal length delta x number I. I need to know this distance because this distance is the radius of the disk that I get by revolving this strip around the x-axis. Of course, I'm going to start on the axis of rotation at y equals 0, and I'm going to go up until I hit the y coordinate that goes with the strip that I'm looking at. I'm on the graph of y equal x squared plus 1. If x is c number I, my vertical extent goes all the way from y equals 0 to y equal 1 plus c number I squared. The vertical height is the upper y number minus the lower y number. In this case, the lower y number is 0, so the vertical height of that strip is 1 plus ci squared. But according to what we said a minute ago, the volume of something like this is pi times radius squared times perpendicular height. If we've been following the previous discussions, you see where this is going. To get an estimate for the total volume of the solid, I'll just add up all of these things, and then to make my approximations perfect, I'll take the limit as all of the delta x's go to 0, as the norm of the partition goes to 0. Having gone through everything that we've already gone through, surely it can't be a mystery to anyone that this is a definite integral, where the limits of integration are 2 all the way up to 5. If I want to actually evaluate this volume, I have to evaluate this integral. This is direct, though. Since doing arithmetic is not what we're about just now, I was lazy, got the calculator out, and 2,197.85822. There's an issue with this that I need to mention. It's not hard to see in general that if you are revolving y equal f of x about the x-axis from A to B, that this same general line of reasoning says you'll always end up doing this. You always end up integrating pi times the square of the f function with respect to x. A lot of times people will memorize formulas. They'll memorize this one, they'll memorize other ones, and then they will misinterpret what it is they're supposed to be doing. I strongly urge you at this stage of the game not to use memorized formulas like this. Instead, draw the picture, figure out what the appropriate rectangle that you're going to revolve about what, and then write the limit of sum. We all know that you're going to end up with this if the case is like that, but if it isn't, life is not so simple. As an example, let's think about the graph of y equals square root of x. I'm going to revolve a piece of the graph under this curve about some axis or the other. If it was revolving around the x-axis, we could already write the integral down, but that's not what we're going to do. I'm going to take the region that I've indicated by putting dots in, the region below y equals square root of x, but above the straight line where the y coordinate's always 1, I'm going to take that and revolve it not around the x-axis, but around the horizontal line where y is equal to 1. I'd like to know the volume of the resulting shape. If all I know is formulas that I've memorized, this could easily throw me, and besides which, the point that we're trying to get to here is understanding integration as an accumulation process. Even though I'm not revolving around the x-axis, I am revolving around a line parallel to the x-axis, so I'm going to split the x-range up into a bunch of smaller pieces. I'm not going to draw those smaller pieces literally on the x-axis, though. I'm going to split them up on the axis of rotation. If I think of all of the points of the region that I'm actually going to revolve that go with one of these little subintervals, one of these delta x's, when I revolve this around the horizontal line y equal 1, I get a disk whose center is along the line y equal 1, not the x-axis. When I revolve that one about y equal 1, I get a disk whose center lies on this line y equal 1, but has a different radius, and so on and so forth. Part of this is exactly as usual. I'll call the horizontal length of one of these rectangles delta x number I. Within each one of those sub-rectangles, I'll select an x, c number I, but here's where I have to be careful. The smallest y number that is in that rectangle is at the bottom. That y is always equal to 1 regardless of the details. The upper y, the higher up one, is the y coordinate on the graph, y equals square root of x, that goes with my representative x number. The upper y coordinate is square root of ci. The lower y coordinate is 1. Vertical heights are the upper y coordinate minus the lower y coordinate. This is going to represent the radius of these sorts of disks. They're the vertical height from the square root function, not down to the x-axis, but only down to the axis of rotation. The recipe says pi times radius squared times perpendicular height. by now, everyone knows we're going to take the limit of the sum of all of those little contributions, which integrates all of the tiny little rectangles together and gives me the actual volume of the shape that I'm after, with the smallest and biggest x values being 1 and 4. Using well-known facts from Algebra and Calculus 1 and omitting the discussion of the arithmetic, the volume is 7 pi over 6 units of volume. Another point that we can illustrate is the point that it's not necessarily always true that x is going to be the independent variable and y is something determined in terms of x. It could be the other way around. This will be especially important if you're going to take the third semester, because beyond a certain point, you're going to have situations where you have more than one independent variable. I want to think about the graph of x equals y squared in the first quadrant. Of course, this is the same as y equals square root of x, but I'm going to leave it like this. I'm going to look at the range of y values from 0 to 2, which makes the x range 0 to 4. I'm going to revolve the dotted in region about a straight line, except this time it isn't the x-axis or a line parallel to the x-axis, it's the y-axis instead. I'm not revolving around x-like axes. Splitting x up into smaller pieces is not going to do anything useful to me yet, although later we'll have a way of doing something with that. In terms of what we know right now, I'm going to have to split the y range up into things. I'll split the y range up, then I'll think about what happens when I revolve each one of those now horizontal strips about not the x-axis but the y-axis. I'll end up with a shape like this. Each individual horizontal strip is going to generate a disk which makes up part of my solid. As usual, the recipe from elementary geometry is pi times radius squared times perpendicular height. If I draw in one of my representative rectangles, this time it's the delta y, and it's this dimension instead of horizontally. Within each such chunk, I'm going to pick a representative value for the independent variable, which is y now. The horizontal strip starts at x equals 0 and ends when x is equal to the x on the graph of the curve at the place where y is equal to ci. The horizontal length is the rightmost x-coordinate minus the leftmost. X is y squared, and y is c number I, so this will be c number I squared minus 0, or c number I squared. So we now know the radius of strip number I. We now know the radius of disk number I, it's ci squared. The perpendicular height is delta y number I, and it's important to remember that c number I is not an x number, it's a y number instead. Aside from the fact that the name of the variable is y instead of x, this should be fairly routine by now. And the limits of integration are the smallest and biggest y values that are important to me. X goes from 0 to 4, but that's not important. The y goes from 0 to 2. So to get the answer to this volume question, all I have to do is do this integral. As I mentioned, it looks a little strange because the name of the variable is not what it usually is, but that doesn't make any difference. It's just a name. I could pretend that y was capital X if I wanted to, if it made me feel any better, which it really doesn't. The value of this volume is 32 pi over 5 units of volume. So to summarize the situation, you're going to have some region in the plane and you're going to revolve it around some straight line, maybe the x-axis or a line parallel to the x-axis, maybe y-axis or a line parallel to it. In any case, draw the picture of the region, draw in the axis of rotation, and figure out whether or not it's going to be vertical strips that generate your disks or horizontal ones. That is to say, is it going to be dx or is it going to be dy? If it's the first one, if it's dx, you have to eventually express everything in the problem in terms of x numbers, and if it's dy, y numbers. If it's like this, figure up the upper y number in terms of x and subtract the lower y number in terms of x. That'll give you some height that depends on x. You'll multiply it later by delta x number I. If the strip is horizontal, it's rightmost x in terms of y minus leftmost x in terms of y. Later, you'll multiply by delta y, add everything up, take the limit, turn it into an integral, and then you do the integral using techniques from Calc 1. In the next video, I'm going to look at a very minor variation on a theme of this. We'll look at the Warscher method. After that, we'll look at the shell method, and that will be about all we're going to talk about in terms of calculating volumes of revolution. Until then, I hope everybody has a good day. I'll talk to you again soon.